Hello, once again. Thanks for joining us. This is Space Nuts. My name is Andrew Dunkley. It's great to have your company. We talk astronomy and space science on this show, and we hope you enjoy it. All 5 listeners have actually said at some stage or another in the last decade that they did enjoy 1 or 2 episodes out of the 618 we've done. So that's a pretty good record. But we'll press on. What we've got coming up for you today is extraordinary. We're going to talk about black holes. These ones, though, are only thought to exist, but they're starting to piece together evidence that they are. And we're talking about primordial black holes. But what's really interesting is how they all began, maybe. We'll get into that. And planets and their chemical makeup compared to their parent star. There's been a major discovery there. And a fresh moon crater, a big one. You could put a couple of 100,000 people in this one to watch a football game. That's all coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And back once again to fill in the blanks is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. I do apologise for my pre-broadcast sneeze there that I hope you didn't pick up on the headphones.
I'll have to listen back, but that's okay. I mean, we've got everything that happens on this show.
Yeah.
I used to actually welcome that stuff on my radio show because I just thought it made everything more human if you had somebody sneezing or tripping over or banging a wall or walking in on you. That was always fun.
Yeah.
But, my philosophy was if you walk in, you're in the show. End of story. Nobody really escaped. How are things, Fred, by the way?
Fine, I think. Yes, I don't know why I sneezed. I think I might have caught the lurgy that you were.
Oh, yeah, I've got a bit of something. We took the grandchildren out and took them to a place called Inflatable World.
Okay.
Jumping castles and slides and, air guns and things. Not the ones that fire lead pellets, but they fire, plastic balls. They had a great time, but I fear, because there were 10 million kids there, and half of them had lots of stuff coming out their nose, I might have caught something. I might have caught something there.
I can't say I've noticed anything coming out of your nose, so you might not have.
Well, just hang around. I'm all dosed up. It dries you out, that stuff. It's good. That's why they've made it illegal.
Yes.
Well, no, it's behind the counter now, I think, is the rule. You can't get it off the shelf. You've got to ask the pharmacist for the good stuff. Right. But it is good stuff. Good stuff. All right, let's carry on. My voice is already starting to fail me. Fred, let's begin, because this is a really exciting story. We have talked many times about black holes, about dark matter, and we've talked about primordial black holes, and now they're starting to think, maybe there's a relationship there. We've got to prove one that might prove the other, which might solve the problem of dark matter. Am I right about that theory?
Yes, you are right, yes. In fact, you've told the story in a much more succinct way than I'm going to now.
Okay, well, that's going to make things fast.
Yeah. So this is a story from LIGO, the Large Interferometric Gravitational Wave Observatory, which has 2 locations, 2 detectors, one in Washington, one in Louisiana. And the first of those detections was quite a number of years ago now. So we've known about these gravitational waves. I think might even have been 2015. I might be confusing it. I do remember it was, the detection was on Marnie's birthday, the 14th of September. So
cool.
I can't remember what year it was. Anyway, whenever it was a good year because for the first time we could sense the collisions of objects colliding in space. Sorry, there's tautology there. We could sense the gravitational wave signal of objects colliding in space.
Yes.
We're both in good form today, I think.
We are. 2015, 14 September 2015. Spot on,
go,
Fred.
Yeah. Thanks. So that was the first time, and the track record of LIGO is incredible. You know, we celebrated the first detection and the second and the third, and then it got a bit routine, and now they just churn them out. But we've had black hole collisions, we've had neutron star black hole collisions, and we've had neutron star collisions. And each of them gives a different sort of gravitational wave signature. And that's the critical thing, that you can tell just by looking at it's almost like an acoustic wave, but it's on a microscopic scale because the vibrations are infinitesimally small, as we've discussed before. Yeah. That's because space is so rigid, but these gravitational waves, as they pass through the Earth, they change the separation of two mirrors in a what's called an interferometer. That's how LIGO works, with tiny, tiny differences. So those waves have because they come in, actually, it's quite interesting. They come in at more or less acoustic frequency ranges. So that if you amplify them up, you can hear it. It's a little bit more complicated than that, but you can actually, it's within that wave band that we can hear things, even though it's sound that we hear, and it's the vibration of space itself that LIGO hears or sees. So what has now happened is that a group of, I think the group is based at the University of Miami, the researchers who've done this work, but they found a signature of a collision that involved a star, or let me put it this way, an object which is a smaller mass than the sun. Now, a black hole that small should not exist in conventional wisdom, because the way we believe black holes are formed is by stars collapsing at the end of their lives as they detonate with a supernova explosion. The core collapses, the outer layers get shed into space, but the core collapses. And you've got a black hole, an object with very intense gravity, because it basically collapses to a singularity, a point in space. Yep. But the conventional wisdom is that you need stars whose initial mass is, 5, 6, 7, 8, 9, 10, perhaps times the mass of the sun. That sort of level, usually 10-ish times the mass of the sun, is typically what you get. And so the black hole remnant that you get has a very similar mass to that. The outer envelope has been blown off, but most of the star's mass basically concentrates into the black hole. So finding a signature of an object that has less mass than the sun is inexplicable. Yes. In conventional astrophysics. It's too small. So what are the possibilities? And the thing that your mind, I'm sure, went straight towards, as did mine, is primordial black holes. And these are objects that were predicted by Stephen Hawking back in the 1970s. He proposed the existence of objects that basically turned into black holes in the aftermath of the Big Bang, where you've got pockets of subatomic material that could essentially collapse directly into a black hole without needing a star to go through, to be formed and go through its lifetime and then collapse at the end of that. But all within, the first, probably less than a second of the universe's existence. Hawking's theory suggests that these black holes were formed. Now, nobody's proved anything yet. They've basically been theoretical entities, and there's been no evidence to suggest that any of them exist. Until now. Yes. Where you have perhaps a primordial black hole being detected with its collision that essentially can only be replicated if one of the objects has less than the mass of the sun. So where does that take us? It takes us straight back to dark matter, because one of the things that was ruled out in the early days of our understanding of dark matter, this is back in the 1970s, late 1970s and 1980s, was black holes. We ruled out black holes because we thought that they would all have masses much greater than the mass of the sun, and that would reveal itself, because if you did a survey like a survey that was done with the what used to be called the 50-inch telescope at Mount Stromlo Observatory here in Australia. This was in the 1980s. That telescope, which is a story in its own right that we haven't time to go into now, but that telescope was used for a survey which was called MACHO. And that's because...
I remember that.
Yeah, MACHO is massive compact halo objects. And what it was looking for was evidence that the dark matter might be something solid rather than subatomic particles, which is actually the prevalent theory now. And by solid, they meant dwarf planets, rogue planets, black holes, things that exist as a compact object that would distort the space around them, so that you'd get this what's called gravitational microlensing effect. You get a magnification as this thing passed in front of a distant star. You get a magnification of the light from that star, which would be detectable by the MACHO experiment and the 50-inch telescope, as it was called. And while one or two of these gravitational microlensing events was found, it was nowhere near enough to be able to use black holes as the basis for dark matter, which is why interest was lost in the idea that this is solid particles, and the whole idea of it being WIMPs, the opposite of MACHOs, WIMPs, weakly interactive massive particles. That's where that all emerges, and that's where we are now. Most of the world of physics believes that there are some atomic particles that account for the dark matter, which of course reveals itself by its gravitational influence, either on the rotation of galaxies or the movement of galaxies in clusters, or indeed the structure of the universe at large. It seems to suggest it's there. So the finding of a primordial, of a less than one solar mass black hole, which would have to be probably a primordial black hole, opens up that possibility again, because if you can find one, there might be gazillions of them out there. Yes. And we might be, misinterpreting what we're looking for. If we're not looking for small black holes, we're actually looking for subatomic particles that maybe don't exist. We have at least one listener to Space Nuts whose name is Pete, who doesn't think they exist, because he's researching one of the alternative theories, the MOND theory, modified Newtonian dynamics.
Yeah, it's really interesting, but it's still kind of a theory, isn't it? I know they've made this detection using LIGO, but they have to confirm it by making another detection, don't they?
Yes, you'd want to see more, and you'd kind of want to start seeing evidence of other kinds. For example, if you revisited the MACHO experiment and looked for the gravitational microlensing signal of tiny black holes that were created in the Big Bang, then that might confirm this and give the idea of primordial black holes being the dark matter. It would give it a much more solid observational basis.
Yeah. Well, it stands to reason that if Stephen Hawking says so, it's probably true. But But it wasn't so long ago that you and I were talking about black holes, and we were saying, look, there's supermassive ones and there's small ones, but there's no in-between ones. And I think within a week or two of us having that conversation, they found one, and now they've found a bunch. So now we're going even smaller, and it could reveal a heck of a lot. Maybe solve some of those mysteries that we've been talking about forever and getting bombarded with in terms of questions.
Yes, which is just as well, because it keeps us keeps us going.
It does indeed. Fabulous story. If you'd like to read about it, it's at spacedaily.com. It's a really fascinating article about a subsolar black hole just changed the dark matter debate, is the title of the article. It's a great title. It is, isn't it? It's a really great read. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
Let's take a short break from Space Nuts to tell you about our sponsor, NordVPN. Now, I've talked about virtual private networks before and how they can protect you online, and no one does it better than Nord. Now, I've been using Nord for over 2 years and I have no complaints. I'm also using some of their other tools, including the brilliant password manager. NordVPN is great for streaming and won't slow you down. In fact, it does the opposite with no interruptions, no limits on bandwidth and no limits on speed. Right now, using the exclusive Space Nuts offer, you can receive 4 extra months for free on a nordvpn.com plan. NordVPN encrypts your internet connection, hides your IP address, and offers access to over 7,700 servers around the world. Plus, with features like Threat Protection Pro, MeshNet, ultra-fast speeds via Nord links, your digital life stays private and efficient. So don't miss out. Visit nordvpn.com/spacenuts and enter the code SpaceNuts to claim this deal. Remember, there's a 30-day money-back guarantee, so it's risk-free to try. Stay safe, stay private, and browse with confidence. That's nordvpn.com/spacenuts.
Roger, your last are here also.
Space Nuts.
Our next story, Fred, is just as fascinating because they have done a bit of an analysis, a chemical analysis on a planet, an ultra-hot Jupiter, and they have made some extraordinary discoveries.
Yeah, these are they're great discoveries because the technology and the techniques required to make these are phenomenal in their own right. But in a way, this discovery should set us all sort of yawning with, well, that's what we thought.
The previous story probably too, but it's too big not to make you go, wow.
Yeah. And this goes wow too,
yes,
but for slightly different reasons. So when astrophysicists think about the planets going around other stars, they basically make assumptions about the raw materials that those planets were made of. And their assumptions come from measurements of the heavy element content in the parent stars. So if you observe a star, you can use spectroscopy to look at the distribution of elements in its atmosphere, sometimes molecules as well if it's a cool star, but usually it's just the atomic elements. And this goes back to the beginnings of astronomical spectroscopy, the idea of splitting the light up into its rainbow of colours and looking for the signature of different elements in it. That goes back to 1869, I think. Might even have been 59 when William Huggins made the first observations of the spectra of stars. So Huggins basically said, well, we know what the signature of elements is on Earth. In fact, some work done by Kirchhoff and Bunsen before that had worked out what the elements were present in the sun were. And Huggins did it. You're going to check up on me here. Is it 1869 or 1859?
1860. Well, there's a few things on the list that involved it, but 1860s is generally the accepted time frame. I think he used Doppler shift to measure the radial velocity of Sirius in 1868, and he specifically identified absorption lines in stellar spectra, including Vega, in 1863 and 1864.
Yeah. So that's not the right time. That's when that's how long we've known about the elements that make up the atmospheres of stars. Most of it is hydrogen, but that's what is the raw material or the fuel that makes stars burn. Or they don't burn, but they have nuclear fusion, which keeps them going. But it's the sprinkling of the other elements that make up the atmosphere of the star, and they vary depending on the temperature and category and age of the star. We measure something called metallicity, and you and I have chuckled before about the fact that
oxygen's a metal.
Astronomers call everything heavier than either hydrogen or helium. Everything else is a metal, including oxygen. That's right, and neon and things like that. It's just a term that came about in probably about the same time as Huggins was working on it back in the 19th century. Anyway, the metallicity is a measurement of the richness in terms of the chemical elements that are in the atmosphere of a star. And so the assumption has always been that if, a star generates its own solar system and that process takes place simultaneously, the cloud of gas and dust collapses into a star, which eventually heats up to the extent that it nuclear fusion occurs, as it is with the sun, but the swirling disk of material around it, called the protoplanetary disk, that stuff is where the planets form. But the planets are basically made of the same stuff as the star is. That's the bottom line. Yeah. So that's always been the assumption, that if we're observing planets around other stars, they must have the same content. And that's critical in terms of whether these planets are going to be rocky or not. If you've got lots of silicate material in it, that would have come from the silicon in the atmosphere of the star. So all these things are interlayered. So that assumption has never been tested until now, and that's why this is a wow story, because this is some observations of, exactly as you've said, a super hot Jupiter. It is, or an ultra hot Jupiter is the technical term. Usually abbreviated to UHJ. So that's a great new term for us, an acronym, an URGE. An ultra-hot Jupiter. It's about 320 light years away. It is called WASP 189b. WASP is, I think, the wide-angle search for planets, if I remember rightly. And it's because it's an ultra-hot Jupiter, the temperature of its atmosphere is ridiculously hot. Yep. It's measured in thousands of degrees. And that means that the materials within it are vaporized, particularly the rock-forming elements like magnesium, silicon, iron, and probably calcium and a few other things as well. They're the things that make up rocks if they're cold. But this one has them in its atmosphere. And the key point about this story, which was led from Arizona State University, along with an international team of astronomers, the key point is that the chemical makeup of WASP 18b exactly matches its parent star. And that is really, that's a kind of smoking gun that tells us that we're on the right track when we make the assumption that the material in a planet around the other star, the material of which that planet is made, will have the same, what we call chemical abundances, the ratios of the different chemical elements to its parent star, which is important information because it means we're on the right track, basically.
I'm going to ask the obvious dumb question here, though. So we've discovered this thousands of light years away with WASP 189b. Why didn't we know that in regard to our own sun and Earth?
Well, we do.
Okay.
That's a good question. We do. But it's never been tested for, what you might call the general case. And an ultra-hot Jupiter is so different from anything in the solar system that it's reassuring that you get the same answer from that as we do from our own solar system. No, it's a great question.
This particular planet is double the size of Jupiter. It's 1.99 planetary masses when you compare it to Jupiter. It was only discovered 5-6 years ago. So it's a new one, but it's 1.619 times bigger than Jupiter in terms of its radius. So it's a monster, isn't it?
Yes, it is. It's some of the planets that we find orbiting other stars are pretty crazy. And
I said thousands of light years. It's 320.
Yes, 300. That's right. That's okay. We'll let you off that.
Yeah. I'm not quite with it today. I don't know how that's different from any other day, but yeah.
Well, funnily enough, neither am I, because I can only hear through one ear at the moment. But that's a minor problem.
Gee, I hate that.
Fixed up.
I hate that. Yeah. One of the pitfalls of radio is you build up a lot of earwax fast, and if you don't keep up cleaning, you go deaf. And then you have to go to the doctor and get syringed. It's not very pleasant. I'm sure people really wanted to hear that.
Yes, that's right. I was thinking that. Yes. But, the stuff that comes out of your ear has the same chemical mix as the stuff that's inside the sun in some remote way. So I'm sure there is a link with astronomy.
Oh, gosh. The article, if you want to read it, it's at scitechdaily.com, or you can read the paper in Nature Communications. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Space Nuts.
And we are going to the moon right now because something happened. It got hit by a big rock, and it's created a massive crater. I mean, this is a very recent development, Fred.
Yes, it is. It's one that comes about, or a discovery that comes about because of our ability to detect changes on the moon, given that the Lunar Reconnaissance Orbiter is still photographing the lunar surface. And it's been doing that. I can't remember when Lunar Reconnaissance Orbiter was commissioned, when it came on stream, but it's quite a few years ago. It's probably a decade ago now. I'm sure you'll tell me in a minute. LRO, as it's called. And because it's doing this sort of continuous survey, we can see when something changes. And in the late Northern Hemisphere spring of 2024, something did change. A rock, probably several meters in diameter, maybe even tens of meters, hit the moon and produced a crater 225 meters across on the surface of the moon. And that is something that we know happens. We expect this to happen because we get bombardment by objects that size of the Earth's atmosphere. They're relatively rare, something like, it will be once every 30 years or so for a 10-meter object to hit the Earth's atmosphere, probably explode in the Earth's atmosphere. But with the moon not having an atmosphere, go straight down to the surface, and what do you get? You get a crater. And it's apparently, this is by far the largest new crater that's been found during the lifetime of the Lunar Reconnaissance Orbiter mission. The last record was 70 meters across. This one's much more, and suggests that this is a much rarer object. One of the reasons I like this story, Andrew, is that it has echoes of something we've just heard about this last week.
The meteorite flashes that the Artemis crew saw. Yeah,
exactly.
So they saw things hitting the moon.
Yes, indeed. And they saw these flashes and that's what they are. And so this one would have been a very big flash. I'm not sure whereabouts on the moon it is, as to whether it was on the Earth-facing side of the moon or not. But it would have made quite a bright flash. And, we've known for more than, 60 years, that these things do happen. It took a while before people worked out that, and before the Apollo era, that people worked out that these were caused by impacts rather than by volcanic activity. I remember old Patrick Moore, the doyen of space communicators in the UK, I remember him. In fact, one of the things he did research on was what he called TLEs, transient lunar events. But nobody knew back in the 40s and 50s whether these were volcanic eruptions or meteorite impacts. Now we know. And we've almost seen them happen before our eyes with this newly discovered crater.
Yeah, and it's a whopper 225 metres across. So, yeah, I suppose you could have a guess at how big the rock that hit it was. What, 10 metres, you think, maybe?
Something, yeah, that sort of order.
And would that
10,
rock still
20.
be on the moon, or did it get obliterated? Because it gets really hot, the impact. It just melts everything and then it freezes instantly or something, doesn't it?
That's right.
Yeah.
Vaporized. It would have been vaporized.
Right.
The energy of impact. This is coming in at 30, 40 kilometers per second. And when it hits rock, I mean, we know from simulations of these meteorite or small asteroid impacts on Earth that the crust turns literally into a liquid, behaves like a liquid. I've got a simulation that I showed only yesterday to a class of physics students at the University of Wollongong online. It's a simulation that shows what would have happened to the Earth's surface with the 10-kilometer diameter asteroid that took out the dinosaurs. And you got within the first 60 seconds, you've got both a hole 20 kilometers deep and a mountain range 20 kilometers high being formed within the first few seconds.
It's just mind-blowing.
Absolutely.
It is.
And so, yes, this new crater, in fact, one of the salient points about it is it is actually quite deep. It's 43 meters deep. There's a nice article about this in Universe Today that makes the point that 43 meters deep, that means the walls of the crater would be steep enough that you'd struggle to stand on them. And so it's got quite a significantly deep object.
Indeed it is, yes. And as Fred said, you can read about that at universetoday.com. And for the record, the Lunar Reconnaissance Orbiter started observing the moon close up in 2009.
Really? That's 17 years now. Yeah. Fantastic.
It's impressive. Yeah. All right. That brings us to the end of the program, Fred. Thank you so much.
Good heavens. Time flies when you're having fun.
Does, doesn't it? Gosh. We'll be back. We'll be back and we'll see you then.
Sounds great. Thanks, Andrew.
Thank you, Fred. Professor Fred Watson, astronomer at large. Don't forget to visit us online while you're out and about or listening to us at our website, spacenutspodcast.com, spacenuts.io. The AMA tab is there to ask us anything. It says ask me anything, but don't bother asking me. But ask me anything, and you can send messages. You can send questions, audio or text. Don't forget to tell us who you are and where you're from, and we'll fix them up in our Q&A episodes. And while you're there, have a look around. Visit the Space Nuts shop. There's lots of goodies in there. It's coming on to winter in Australia, so you might need yourself a hoodie. You can look like a thug and be an astronomer at the same time. Fred does. And damn, I should. No, I usually have a crack at Hugh, but he's not an astronomer. But yeah, and thanks to Hugh in the studio, who couldn't be with us today. He's once again in police custody because they found a giant, I'm saying, slingshot in his backyard aimed at the moon.
Ooh.
Oh, yeah. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.